Hi there, my name is Rich Hunt. I work at Sandia Labs. I want to talk a little bit about a research project that we did a couple of years ago, kind of incrementally trying to improve pieces or different areas of our software over time. This particular area was to develop what we call a data-driven command and telemetry capability for the software. The goals of this research was one was to create what a modern version. I think a lot of people are doing this already, but and we've done it in the past, but it was to kind of bring it forward into the next generation. What we call the Electronic ICD, where you can define all your command and telemetry parameters and share that ICD with all of the different subsystem teams within a project, all the way up through the end users. To get better coherency between all the teams, making sure they're using the same definition. Further was to develop software that would automatically use that electronic ICD within the flight ground software in what we call a data-driven fashion. So we would automate a lot of the software generation and operation within both the flight and ground systems. Next was to show how you could use COTS-based tools to manipulate the data within the flight and ground systems. And then finally we created a small demonstration around this on both a representative flight computer and a ground system to kind of demonstrate all the work we'd researched. These are just some of the terms that I'll be using throughout the presentation. I put it in there for reference purposes. We'll talk about some of them, but I wanted to make sure they were in there. All right, so what is an electronic ICD? In the really old systems, right, you used to write an ICD in a paper version, right? You distribute it to all of your teams, and then they'd go off and they'd start coding, and you pray to God they'd all come to the end and have the same interpretation, and everybody's software would play nicely together. Back in the early 90s, we got kind of tired of the cycling through all that, and so at Sandia we developed some software where we could define all of our command and telemetry interfaces we did it in an ASCII-based file. And not only did we define, the basic parameter types, but we also defined all the hardware registers for accessing those parameters within the flight hardware. And so we put all that into this monster configuration file. In fact, I think we printed it out once that was like 15 stories tall. We then developed a compiler that would go through and parse that ASCII file and would actually generate all of the data structures that we could then include, of course, within the flight software for storing all the command and telemetry information. And so all that code was auto-generated. The ground systems would use that file directly to dynamically build all their displays. So they basically built, they wrote code for all the basic data types that were in the config file, and then on startup they would ingest that file and dynamically build all their displays. And again, this was all back in the early 90s. And so what that created was a very tightly coupled flight and ground system. We'd make one change to this electronic file and we'd go restart the ground system. We did have to recompile the flight software, but we knew that they were tightly coupled. So it really reduced the amount of testing and the cycle time between making changes to the flight and ground systems. Okay, and so the goal of this work then was to kind of bring that forward to the next generation. So we created a new version of the electronic ICD using the modern electronic document standards, XML, along with the XTCE schema. We used what they call XML Data Binding tools that allow us to use that XML data within the software in what we call a data-driven fashion, and I'll get into that a little bit more. And then since it's all XML based, we could operate, develop the ICD through a web-based interface, very easy for all the teams to get access and have a common reference, without having to ship paper documents around. Okay, so a little bit, I think most people know what XML is, Electronic Document Standard, developed back in the 90s. Very easy way to share information between different computer systems across the internet. Files are ASCII readable and machine readable. Lots of tools out there to parse and use XML data. The XML Telemetric and Command Exchange XTCE schema is both an OMG and a CCSDS standard, developed in the mid-2000s, basically defining all of the schema definitions or data types that you would use within a space mission, including all the commands and all the arguments that you might use with that, all the telemetry along with all the mnemonics, all the configuration values or configuration parameters, alerts, alarms, all the thresholds, things like that. And then as well as all the packaging, all the packet definitions and wrappers, major and minor frames. And so that's all within that schema definition. I'm sure this is not readable, but this is just a high-level look at what the XML, the XTCE schema looks like. At the top level, they have all the definition for all the containers that you can build all your packets and frames out of, and then drilling down into the command and telemetry, you can see all the basic data types, if you could actually read that. Next, XML data binding. So this is the process of generating software objects in computer memory from the XML data itself. And this is where it got really pretty interesting. This is where we, that config file we did in the ASCII file, that was a very static thing. We compiled it, we linked it in. Here, using the XML data binding compilers, we can do everything at runtime now. So it's all dynamically configured at startup. Which really makes it much easier. Now we don't have to rebuild the software every time we want to make a change. XML data binding compilers they provide the ability to parse XML files, serialize and deserialize data in and out of the data structures that they create, as well as provide the validation functions for checking your XML files to make sure they're correct and they adhere to the schema. There's data binding compilers for a number of programming languages, C++, Java, or there's a couple examples, as well as supporting a number of operating systems, including embedded operating systems. We're using VxWorks right now. I'm sure you could probably compile it for RTEMS. I haven't done that yet. Okay, so what is data-driven software? So this is software that's automatically generated or operates on the metadata within the electronic ICD. So one example is like I said before, when the software starts up, it will ingest the XML file. The XML data binding tools will then automatically build dynamically all the data structures that you use to store the command and telemetry data within the flight system. Some other features of how the auto-generated code can be used from the metadata. As I said, the memory structures. We've also demonstrated that you can build the database structures from this. All the GUI displays, so all the ground system displays, again, dynamically built by ingesting the XML file in startup. And then what are some of the software functions that can operate on the metadata? So telemetry collection. Some of the features that you can put into the telemetry definition are update rates. How often do I want these tables to come down? And when the software starts up, it will automatically build a scheduler based on that and can downlink your telemetry tables. Data validation, so when data is received by either the flight or ground system, put into what we call the data model, it's automatically checked to make sure it matches the appropriate types and sizes. Database population, GUI population, so all those interface functions can be auto-generated at startup. And then the communication link, encoding, decoding, so this is basically creating your command and telemetry streams by parsing the data model in memory. And it can auto-generate all the packets and everything that come in and out of the software. All right. This is kind of a graphical representation of what I call the developer-driven approach versus the data-driven approach. It gives a little better example of some of the advantages of using this data-driven concept. So the boxes in red represent areas where, and this is kind of the worst case, right? Assuming we had a paper-based ICD. Boxes in red represent areas where the software would have to be touched by a developer if you made a change to the command and telemetry definition. And then the boxes in green represent where the software automatically is either generated from it or it adapts to it at runtime. And so there's no changes that are required. So in the legacy or in the historical systems, we had a paper-based ICD. You'd have to go in, and developers would have to change memory structures to support new parameters that you might add. You'd have to change your command and telemetry encoders and decoders to create the packets that would go between flight and ground. You'd have to change some application code that may be using that new parameter that you're adding. And then finally, you'd probably have to change your ground system displays to support that parameter you added. Using a data-driven approach, a little bit different, you may or may not have to change your applications depending on what you're adding. If you're adding maybe just a new telemetry feature, I want to get, what's the status of this hardware register. You may already have the software on board that knows that's written to, read hardware registers. Well, you add one more hardware register and it can already use that. And so that's an example of where you wouldn't even have to change an application. But, if you have something that's manipulating data on board, I get it. You'll have to go and you may have to change an application in the flight software. But you would basically make the change to the XML data file. You would load it, restart your flight software. And so, the nice thing is now I don't have to upload, a megabyte file of flight code. It's a 20K, XML file to make that kind of change. When the software starts up, the memory structures get allocated, the encoders and decoders automatically adapt to that new parameter, and then again, restart the ground software, it automatically adapts, and we'll display that. Okay, this is a representation of our electronic ICD that we generated for this, as well as the XML output. The nice thing is all of the entire web-based interface that we developed from this, it was all auto-generated from the XML itself using the same tools that we would use to make ground system displays. So we had a piece of software that would ingest the XML file, build the web pages, and the web interface to reflect that XML file to users. You could then create new tables and new parameters, and you could save that out to the XML file, and again, they keep moving on from there. So again, a lot of auto generation. That's kind of one of my goals is to reduce the amount of handwritten code that we have to develop. And in some areas, I've looked at some of our legacy systems. The areas that we're touching, you're talking maybe 25 to 50% of your flight software. Okay. Not only can you generate the XML, but from that XML definition, you can generate PDF documents. And so, you're still going to need those for documentation purposes. This was like the out-of-the-box PDF converter for an XML file. And so this is a telemetry table. It has all of the units and the conversion values and thresholds. And so we just did a basic dump to a PDF file, and it prints them out. It's maybe not the prettiest thing, but with a little bit of work, you can format that PDF file and make it pretty nice. And so that's something that's fairly easy to do. Okay, some of the benefits of the electronic ICD, then, to summarize, is that it allows the content to be conveniently managed through a web interface and shared amongst all the teams. Payload and ground system applications stay very synchronized, right? If they're working on the same version of the electronic ICD file, they're in sync, and they will be able to communicate back and forth. It enables sharing of data between different teams and organizations, so you can distribute your data as long as they have that electronic ICD and some XML tools, they'll know how to parse that. The content can be automatically validated against the schema, so when you load that XML file and the data gets stored in your code, it meets the schema standards. And then the data can be outputted in a variety of formats. Some of the benefits of using a data-driven approach: it reduces the time to develop, integrate, and test software due to the whole dynamic and auto-generation and auto-use capabilities. So you validate that software once when you first develop it. You check it to make sure it can support all the basic data types, but then once you add another parameter of those data types, you shouldn't have to check that software again. Reduces the risk of programming errors. So now we don't have developers on all these teams going in and editing all these different pieces of software for every time a change needs to be made. And then finally, it reduces the risk of large application uploads. Depending on the change, it may be as simple as uploading a 20K XML file. Okay. Next couple of slides just kind of show the process of how this works. So the first thing you would do is define your schema. So we went to XTCE. It's a very broad standard, supports a lot of different things. I heard you guys talking about it the other day. I was listening in. And so we did the same thing, right? We pared it down to what we needed. And, and that drives the size down. I want to say the image in our flight software is on the order of a few hundred K when we build our data model. So it's fairly compact. So you define your schema. You use the XML data binding tools to create a data model. That gets built into a library and gets linked. That's the only piece that gets linked into the flight and ground software. And so once you define your schema with all your basic data types, you should never really have to change that again. And so that should be fairly stable. Okay, so next you would define your electronic ICD in terms of that schema, right? And so you define all your command and telemetry types. The next couple of steps are something that we would use on the flight software in order to compress the data down. And so you can use the data binding tools to serialize your data into the XML data into a binary form, and that's the form that we use in the flight software as a configuration file for the software. The ground systems can use the XML, directly. They can have multiple copies. They got tons of memory, right? Workstations. In the flight software, we have one copy that we store in memory, and all of the different software applications then would access that one data model. When the software starts up, the software will read the electronic ICD. Again, the data binding tools will populate this data model in memory, and then the applications will start up and be able to use data within that data model. So all the command and telemetry data is getting populated into that data model. Right, initially it's all your initial values, things like that, and as new data comes in, applications then can write data into that data model. All your telemetry generators can go and parse the data out of that data model and create the packets to go to the ground. Things like that. Real simple system here of how you would send commands. So I'm showing a common data model here with dashed arrows. That kind of represents they're virtually using the same data model because they were using the same electronic ICD, but ground system operators would generate a command. They get populated in the data model. You have some sort of command processor then that's going to create a command packet out of that. It's going to get wrapped in a flight to ground protocol, sent to flight. It's going to get stripped out of the protocol. The data is going to get validated and populated into the data model. And again, depending on the level of metadata you have in there, you could put in hardware registers and everything. Your command processing software then can automatically know how to, what memory register to write to and what value to put into that with no changes. Same thing on telemetry. Again, I talked about putting scheduling values into telemetry tables. Well, you can have applications writing telemetry data. They'll be storing it within the data model. They'll be, they could potentially be notifying a telemetry application to send data down, or they could be scheduled to go down. The data gets extracted, sent through the flight to ground protocol, populated in the ground data model, and then the operator displays would automatically get updated from that. Okay, lastly, so we created some software to demonstrate this, both flight and ground software. We had a basic sensor data processing algorithm that would generate telemetry, populate a data model. We were reading the data out of that, generating the telemetry packets going to the ground. The payload could also accept commands, populate the data model, notify the algorithms, turn them on, turn them off, change rates, things like that. On the ground side, same thing. We had the GUIs that were all auto-generated from the XML definition. You generate commands, transmit them up, receive telemetry, populate them. We also spent some time demonstrating we could auto-generate an entire database as well as all the interfaces to automatically populate it with the data. And then finally, we developed the flights version, or the flight software, in C++, and we ran it on one of our processor modules. It's based on the Leon 3FT, running at 80 megahertz. We had 32 meg of RAM. Like I said, the footprint of this was on the order of a few hundred K in memory. So you can see these are all kind of basic embedded flight system parameters here. We were using Ethernet as our command and telemetry link between the workstation and the flight processor. Again, C++ running under VxWorks. We used the code synthesis. XSD was our XML Data Binding compiler for C++. On the ground side, all the ground software was developed in Java, running on a Linux workstation. Using the JDK, we use Jaxby as the XML Data Binding compiler on the ground. JavaFX and ControlsFX for all the GUI generation. And then we used RMI to communicate between the different JVMs running on the ground. And that's it. Any questions? Yes, sir.
Where's it? Mike, yeah,
So any thoughts on configuration management of your XTCE against your data sets and telemetry
Yeah,
commands?
so that web interface I showed you is built on a whole back-end CM system, or at least that's where we're going with it, right? And so that will be going on behind the scenes. And so as you're, interacting with that web interface, it's configuration managing all of the output, all the XML files that are outputted from it. So.
for those of you that are interested, the Aerospace Corporation actually has a tutorial on this put together by Jerry Simon. You know Jerry?
I don't.
He's largely responsible for XTCE.
Okay.
He wrote much of it.
Okay.
Anyway, it's a huge tutorial, but if you check the GSAW website, he gives it every so many years, and it's long. But he has lots of good examples with a trivial set where you sit down and you write the XMLs.
Yeah, we worked closely with Kevin Rice on that, at the GSAW conference and things like that. And the one thing that was kind of unique to this, I think, was the whole XML data binding process.
Yep. Nobody
had really kind of been doing that yet, and so that was just something we were doing in our old systems, and I wanted to figure out how to do it using XML files.
One little quick comment. I just say, you're probably aware of the CCSDS EDS work out of this.
Yeah, I listened in on a lot of those.
So there's some parallels here. You're actually trying to solve sort of different problem just on the command and telemetry side, not the data exchange between software modules.
Right.
So really the thing would be, we could talk about with Kevin Rice, because he's on our team, is how you could ingest an EDS to then inform.
Yes.
Because our EDSs actually generate, software drivers and the header files for all the software, because the G and C actually have to interpret the data.
Right.
You can't do that on the fly.
Yeah, I know they were taking it to a whole nother level with the whole behavioral aspects and
But
some of that.
it sounds like you got some very nice tools that we could also leverage.
Yeah.
Since I'm assuming these are going to be open, or they are, since they're government funded, or?
I don't know. That's a good question.
Okay.
We can talk though.
Yeah.
Government funded doesn't mean open.
Well, we have to work at it.
Yeah. No, we can certainly talk about that for sure. Absolutely.
Actually, if you get in touch with
Yeah,
Jonathan, we had we had a volunteer meeting every Friday, like for a year, helping Goddard to push things out the door, and they were very successful.
Nice.
Anyway, so thank you very much.
Okay. Sure.